All right, let's run through this Unit 1 review here. On number 1, we have an explicit definition of a sequence, and we are asked which of the following is the recursive definition. So we need to look at a few different parts of our explicit definition. Here, our domain tells us our starting term. If I plug 0 into my function for n, I can see that f of 0 would be -4 plus 2 times 0. Well, that would be -4 plus 0, which would be -4. This tells me that my starting term, or term 0, is -4. So right off the bat, I can eliminate A and C. All right, I see that B and D are the only ones that have a starting term of -4. So now if I look at the next part of my recursive definition, I see that this says to get the current term, take the previous term plus 2 times the term number. Right? This one says to get the current term, take the previous term plus 2. So if I'm thinking about my explicit definition, this is saying to add 2 repeatedly, or add 2 each time. Again, if I were to start plugging in values, right, if I make a table, term 0 is -4. My term 1 then would be, well, if I plug 1 in here, -4 plus 2 times 1, or -4 plus 2 would just be -2. And then if I plug in 2, I would have -4 plus 2 times 2, or -4 plus 4, that's 0. So I can see that I am just adding 2 to the previous term. I am not adding 2 times the term number. So that is why the correct answer to number 1 is D. All right, on number 2, we have the recursive definition. I want to come up with the explicit definition. So if we examine here, I can see that my term 0 is 5. My starting term is 5. That is a big part of the domain on my explicit function. Right? This tells me term 0 is 5, so I know that I'm going to have to start with a domain of n is greater than or equal to 0 to satisfy my term 0 being my starting term. So I can eliminate A. Right? That would mean I'm starting with term 1. Now, if I look at this situation, okay, I've got 5, and then my rule tells me to repeatedly multiply by 1/2. Again, we could build a table to kind of see this happening, starting with 5 and then repeatedly multiplying by 1/2. But hopefully we're able to recognize that starting with 5 and then multiplying by 1/2 would end up being C here. Now, I mean, I can build out the table here. Right? So at term 0, my answer is 5. If I multiply that by 1/2, I could say that that is 5/2. Now, we've talked about another way of writing that would just be my starting term of 5 times 1/2. Now, my next term then would be 5/2 times 1/2. That would end up being 5/4. But again, we've talked about another way of writing that is 5 times 1/2 times 1/2, or 5 times 1/2 to the second power. And again, if we continue this pattern, we'll be able to see that repeatedly multiplying by 1/2 means I'm going to be raising 1/2 to a power. In this case, that power always matches up with the term number. That's why my exponent is just an n here. Right? If I'm on to the nth term, then my exponent would just be an n. All right, on number 3, this one, similar type of problem as 1 and 2. This time we've got a pattern of blocks, and we want to look at all of the definitions that satisfy this pattern. So it might help if we just look at the number of blocks. Right? In step 1, I've got 4 blocks. Step 2, I've got 6. In step 3, I've got 8. In step 4, I've got 10 blocks. So we can see the pattern is we're just adding 2 every time. And I'm starting with 4 and adding 2 every time. So which of these sequences satisfies that idea? Well, on A, this is saying I'm starting with 2, right? That's how I would interpret this one. This one says my starting term is 2. So A doesn't work. B, this says my starting term is 1 and I'm adding 3 every time. Well, that's not going to work either. C says that my starting term is 4 and then I'm adding 2 every time, but I'm starting with 1. So if we plug 1 in, right? I mean, this one appears to work, starting with 4 and adding 2 each time. But if I plug 1 in here, 2 times 1 is 2 plus 4 is 6. This formula tells me that my first term should be 6. That's not true, right? So even though this one shows first term of 4 and adding 2 each time, this one is technically not correct because based on this definition, I would get term 1 is 6, and we know that term 1 has to be 4. On D, this is a recursive definition, and this says term 1 is 4, and to get the current term, take the previous term plus 2. Well, that works. And then my domain does show that since I'm given the first term, that I should continue the pattern by plugging 2 into my rule. That one does satisfy all the parts that we need here. E, another recursive definition, but this one says that the first term is 2. So right off the bat, I know that that is not correct. And then the last one, this explicit definition says that my first term is 4, and then I'm adding 2 each time. This time they used n minus 1 instead of n. Now let's check to see if we get our first term of 4 by plugging 1 in for n. So if I plug 1 in here, 1 minus 1 is 0, 2 times 0 is 0, and 4 plus 0 would be 4. So this formula does get me 4 as my first term, right? So that's the difference between F and C here. These were very closely related formulas. They were just off slightly because of how the function was defined. Since I'm starting with term 1, technically we needed the n minus 1 in order to show that our first term was 4. All right, number 4, we are given a partial table of an arithmetic sequence, and our goal is to write a recursive definition. So we need 3 parts here. Now the key on this one is that we are missing some terms in the table, right? So if I start listing these out, I know my first term is 2, but then I don't know my second term, and I don't know my third term. I know my fourth term is 6.5, and then I don't know a bunch of terms. I don't know term 5, term 6, term 7, term 8, but then I know term 9 is 14, right? So this is basically the data that we have in the table. I do know that this is an arithmetic sequence though, so that means I'm going to be adding the same thing each time. The key for a problem like this is looking at the difference between 2 of these values. So to go from term 1 to term 4, I'm going from 2 to 6.5. So I'm jumping a distance of 3 terms. If I take that difference between 6.5 and 2.5, so if I subtract 6.5 minus 2, that gets me 4.5. But that's over 3 terms. So what I would need to do is divide 4.5 by 3. So if I divide 4.5 by 3, if I put that in the calculator, that comes out to 1.5. That means that my rate of change is actually 1.5. And we can test that, right? Let's make sure that that works. So if I do 2 plus 1.5, I get 3.5. 3.5 plus 1.5 is 5. 5 plus 1.5 is 6.5. So it checks out. That works. So now with that information, we can write our recursive definition. So I can say P of 1, because my starting term is term 1, P of 1 equals 2. Then to get the next term, we'll say P of n equals P of n minus 1. Just take the previous term and add 1.5. And then the final part, the domain, since I started with term 1, to continue the pattern, the first value I would plug into my formula is 2. All right, number 5 is a multi-part problem. We've got a piece of paper that is 125 square centimeters, and we are cutting off a strip that is 1/5 of the original size each time. And then from that piece, we're cutting off another strip that's 1/5 of that area. So essentially, we are multiplying by 1/5 each time. All right, we can see that we're not subtracting or adding the same thing each time. What ends up happening is we are multiplying by 1/5 to get from one step to the next. And we can see in our graph that this models exponential decay, right? The table and the graph both represent this same function. So to answer the first question, we can say that this function is geometric. And then because, right, our explanation would be we are multiplying by the same thing each time, right? We are multiplying by 1/5 to get the next term. And remember, in order for a sequence to be geometric, we have to be multiplying by the same thing each time. So we can't just say we're multiplying each time. We have to be specific and say we are multiplying by the same thing, by 1/5 each time. So now I want to write an equation to define this both recursively and explicitly. So first, recursively, I need 3 parts. I need to give my starting term first. So in this case, if we look at the table, we see that our starting term is term 0. So I can say C of 0 equals 125. Then define the rule. So to get the current term, take the previous term and multiply by 1/5. And then the domain, n is greater than or equal to 1. Again, because I give you term 0, then to continue the pattern, the first thing I'm going to plug into my formula is 1. Now, let's write an explicit definition. So to define this explicitly, if I'm starting at 125, I can say C of n equals 125. And then my growth factor here is 1/5, so times 1/5. And if I'm repeatedly multiplying by the same thing, that's when I use an exponent. That's when I can raise that to the nth power. And then again, the domain is just going to be whatever my starting term is, right? This tells me what term number to plug in first, and the first term we're plugging in is 0. So that would be my explicit definition. Now the last part here asks for a reasonable domain. How many times could I reasonably cut this into strips that are 1/5 the size, right? So, I mean, we can already see as we get down to here, as we get down to 4 cuts, that I'm already down to a piece of paper that is 1/5 of a square centimeter. That's already really small. So in this case, I might actually say that I can't go any further than 4. Now, I mean, we might be able to go further, right? We could say at the 5th cut, we've got 1/25 of a square centimeter. So again, there's not always a single correct answer to a problem like this, right? We probably could say 4 cuts or 5 cuts, but I don't think we can go anywhere past that, right? That is a very, very small piece of paper, and it's probably not feasible to cut 1/5 of that off very accurately anymore. So here, right, if we want to write our domain in a compound inequality, I could say that the number of cuts has to be greater than or equal to 0, but less than or equal to 5. And again, don't forget to explain your reasoning, right? So I could say something like, it's not reasonable. So let me type this out so I don't have to write it. So we could say it's not reasonable to cut a piece of paper into fifths that is 1/25th of a square centimeter, right? Something like that. Okay, just a short explanation of why we can't go any further. All right. Now, on number 6, we are given the first two numbers of a sequence, and we need to write a recursive and explicit definition if that sequence is arithmetic, and a recursive and explicit definition if that sequence is geometric. So, first of all, if it's arithmetic, we're thinking we're adding the same thing each time. So if this is arithmetic, and I'm going from 4 to 12, I would be adding 8 each time. So first, my recursive definition, we would start with my starting term. So in this case, they tell us term 0 equals 4. Then my rule we said is add 8. So to express that, I would say m of n equals m of n minus 1 plus 8. And then my domain, since I gave you term 0, my domain would just say, well, the first value I have to plug into my formula is 1. For my explicit definition, I want to think about my starting term and my rate of change and define a domain. Now again, we've kind of built our understanding of explicit formulas through tables, right? But the idea here is, or the pattern here is always going to be the same. It's going to be starting term plus my rate of change times either n or n minus 1. In this case, this will just be n because I have term 0. So if I define my domain starting with my starting term, n is greater than or equal to 0, and I test this, right? If I plug 0 in for n, 4 plus 8 times 0 does in fact get me 4. For my geometric sequence, if I take these first two terms and say this is now a geometric sequence, then my pattern to get from 4 to 12, I would be multiplying by 3. Now remember, we can easily test that, or not test that, but easily find that growth factor by taking a term and dividing by the previous term. So if I take 12 divided by 4, I get 3. So that is my growth factor. So to write all that out, I can again give my first term, say m of 0 equals 4. But now if we're defining this geometrically, I can say m of n equals m of n minus 1. Remember, this is just current term equals previous term, and then my rule here is times 3. Again, just like my first one, my domain will be n is greater than or equal to 0. That is just going to be 1 greater than my term number, my starting term number. Then for my explicit formula, if I am repeatedly multiplying by 3, that's where I'm going to use an exponent. So I am using my starting term again, 4, but then times my growth factor, so 4 times 3 to the nth power. And again, in this case, since my term 0 is my starting term, I'm going to define my domain as n is greater than or equal to 0. This just tells me the first value to plug in. All right. Now, number 7. On this one, we are walking on a dock, and Cameron walks 1/4 of the way across the dock and stops. Then he walks 1/4 of the previous distance. So he's not walking 1/4 of the entire distance the second time. He's just walking 1/4 of the 1/4. All right, and then he continues that pattern. So after he's done this twice, well, the first time he walked 1/4 of the way, and then the next time he walked 1/4 of the 1/4. Okay, so 1/4 of 1/4, well, that would be 1/4 times 1/4, or 1/16. Now remember, to add fractions, we would have to get common denominators. So to get common denominators, I can multiply this one by 4/4. That would give me a denominator of 16. So this would become 4/16 plus 1/16. So after 2 times, he has covered a distance of 5/16 of the dock. Now, I did this by hand, but we could just plug this into a calculator. I could do 1/4 plus 1/16. Just make sure that you are giving your answer as a fraction, not as a decimal. Make sure you're giving your answer as a fraction. So now, if we calculate this after 4 times, well, that first distance of 1/4 plus 1/16. Now, my next would be 1/4 of the previous distance, 1/4 of 1/16. So 1/4 times 1/16 ends up being 1/64. And then my fourth distance, or the fourth distance that Cameron travels, would be 1/4 of 1/64. That ends up being 1/256. Okay, so here, again, if I wanted to try to do this by hand, I would be multiplying to get common denominators. I would be multiplying my first one by 64 over 64. So that ends up being 64 over 256. This one I would be multiplying by 16 over 16, so plus 16 over 256. This one by 4/4, so plus 4 over 256. And then finally, that one, last fraction, is already a denominator of 256. So if I add all these together, 64 plus 16 is 80, plus 4 is 84, plus 1 is 85. Now again, I did this by hand. You could plug these into the calculator and get this fraction, 85 out of 256. So that is the total fraction of the dock that he has traveled. So the last question, will Cameron ever actually reach the end of the dock if he continues this pattern? Explain your thinking. Well, we're not even halfway, right? He's only gone 85 out of 256. Halfway, half of 256 would be 128. So we're not even halfway, and we're continuing to add a much, much smaller value each time. So Cameron will actually never reach the end of the dock if he continues on this pattern. And we need to, again, explain our thinking. So we could say, no, he will never reach the end, and we could say something like what I just said. We are adding a much smaller value each time, and eventually that value is going to be so close to 0 that Cameron's basically not even moving. Right? He's never going to reach the end of the dock in this case. All right, number 8. We have 2 different sequences here, sequence A and sequence B. For both of them, I want to write both a recursive definition and an explicit definition. Remember, this language here, a definition for the nth term, means write an explicit definition. So let's go through A first here. We're given a table, and we can see from the table that we end up multiplying by 1/3 each time. Okay, so 9 times 1/3 is 3, 3 times 1/3 is 1, and so on. So first, for my recursive definition, I can say term 0 is 9, so A of 0 equals 9. And then my rule, we said, was multiply by 1/3. So to express that, current term equals previous term times 1/3. And then my domain would be n is greater than or equal to 1 because we're starting with term 0. Then for my explicit formula, to express that we're starting at 9 and repeatedly multiplying by 1/3, I would say 9 times 1/3 to the nth power. And again, since we're starting with term 0, my domain is n is greater than or equal to 0. For sequence B, we're given this graphically. Now, just by looking at the graph, I can get my terms, right? I can see this first one is 13, then 9, then 5, then 1, then -3. So my pattern here is -4 or subtract 4 every time. And we can see that it's going to be an arithmetic sequence because it is a linear pattern on the graph. So if my rule is subtract 4 every time, to write that recursively, I can say b of, now this time we are given that my starting term is also term 0, right? It's on the axis, so that is term 0. I can say b of 0 equals 13. And then my rule was subtract 4, so to get the current term, take the previous term minus 4, and again, the domain will be n is greater than or equal to 1 because I give you term 0, so the first value I need to plug into my rule is 1. My explicit formula then, since this is arithmetic, to show that I am repeatedly subtracting 4, I would say, well, my starting term is 13, and then I'm going to subtract 4 times whatever term number I'm on. And then again, n is greater than or equal to 0. Remember, for a geometric sequence, I will be raising my growth factor to a power. For an arithmetic sequence, I will just be multiplying my rate of change times n in the explicit formula. All right. The last part then just says which one is greater, a of 6 or b of 6. So based on the formulas we wrote, we could actually find these values, right? Or we could think about it intuitively. If I continue taking 1/3 of this value, of the previous value, I'm never going to get to 0. I'm going to keep getting closer and closer to 0, but I'm never going to get to 0. Over here, if I keep subtracting 4, I'm already into the negatives, so I'm going to keep going further and further down. So this one won't even be past 0. This one will be into the negatives. I can say that b of 6 will be less. Now again, we could actually just calculate those values. We could say that a of 6 equals 9 times 1/3 to the 6th power and calculate that out. So what would that be? 1/81 if we put that in the calculator. And then b of 6, again, we could calculate that and say 13 minus 4 times 6. So 13 minus 26 would be -11. So again, we've shown that b of 6 is less, a of 6 is more. So make sure that we state that, right? Make sure that we say that a of 6 is greater than b of 6. This would be a legitimate explanation, just showing what they're equal to, or we could explain something like what I just said, like sequence A will never be less than 0, whereas we can see sequence B is already less than 0. So that would be another possible justification.